Okay, welcome back. And we're getting started with the discussion session. So 1 hour to grill our speakers of this morning. Any questions?
Well, just like a persistence issue I raised before about the last talk. What goes wrong if one of these bounds is violated? What happens to the theory something is violated? You're just saying you don't like causality violation, and I guess I don't either because we don't see it. But suppose the theory was manifesting it, would it be like, let me give you an example. Suppose we have a Higgs potential, right? For a period of time, it will develop, when it makes a transition, a symmetry breaking transition, it will develop a tachyonic mass. That's, of course, not a causality violation. That's an instability. And what happens is that the theory then decays to the symmetry breaking vacuum. What is there something analogous that happens in these theories, or is there some instability that develops?
I mean, from my perspective, I wouldn't be okay if I can measure at any distance or time that I send in a wave and actually there's somewhere it scatters and it comes out before it actually reached the scatterer. So that's basically what these violations of causality tell you, that if you send in a wave, it reaches the scatterer. If there's a causality, it actually exits the scatterer before it arrives to it. From my perspective, I will just say that's unphysical. If you were okay with having that at certain distances, I guess you could formulate.
You know, you do see things that, if you didn't believe in primordial inflation, would be acausal correlations in the early universe. And one alternate explanation has always been that there is a phase where that's allowed.
Sure. I guess it comes to a choice of what you believe it's physical or not, or what you allow or not. What I will only allow would be something that is not measurable, of like this uncertainty principle, like 1 over omega or 1 over lambda relations. But I think it's just a choice. What else goes wrong besides a causality breaking down? That I don't have the answer to. That might be a model dependent thing. But if it, as you say, maybe the universe happens to behave that way in the early universe and you actually have violations of causality there, and for the rest, and what we've been seeing is just causal. Maybe that's what it is. From my perspective, what I'm saying is this is my physical principle. This is what I believe should happen.
Any follow-ups on that? Or new questions? Luca.
It's just a question comment on your interpretation of the quantum correction to the three-time potential.
Yeah.
I think it's what we imagine, like saying that there is some uncertainty in position, so you fix time, you expect correction. But if you follow the logic, the expectation correction proportional to h bar, it goes like 1 over r squared. But you don't have that, because I think the first term is 1 over r cubed.
Yeah.
So I don't know if it's really so simple to interpret this.
I mean, it's more like a toy way of interpreting. But if you start with, say, Newton potential, it's 1 over r. And you say that there's some, I mean, we do associate quantum gravity with some kind of non-locality. So if there's some non-locality effect, which is our choice of thinking about quantum gravity, it's somehow signaling that there is something like this in the computation. But the way it comes about, of course, is more intricate from the way we deal with the path integral and stuff like that. But we do see a clear distinction between the classical pieces and the quantum pieces once we start analyzing things in terms of this iconal. So for the iconal, you can see the classical piece as being the piece that actually corresponds to sort of a steady state solution, like like it's a propagating wave, but there will be some kind of a classical expectation value of that wave, and the uncertainty, the quantum uncertainty associated with that is what's associated with the phase that sits outside. So I mean, nobody has pursued this, but I know John has some comments along the same lines as I made in the talk in this paper. So
I have a technical question.
Yeah.
It's too technical, you can just.
That's okay.
Large discussion. So, I mean, I would like to compute gravity vertices
yeah,
in all tensor structures.
yeah,
So, for example, for the 3-point vertex, it's something like 36 tensor structures.
yeah,
So it's not only the ones you get from the Einstein-Hill vertex.
yeah.
The amplitude approach, is it helping there?
I
Or
think
is it-
I mean, things like unitarity should be like, you want external particles to have, say, more structures like
in a way, you can describe a scattering process of 3 gravitons.
yeah,
And let's assume you just do a Lie expansion.
Yeah. Mm.
And now I would like to represent the result in terms of general tensor structures.
so you use it would be covariant dot product. So
They're covariant, but they are gauge dependent. So you really need, I mean, that's why I say, I mean, at the very end, you have a complete basis. If you go to the standard call it, what you call the final the diagram approach, you would have a complete basis of tensor structures order of magnitude value.
but what I mean is, so you say they're gauge dependent, meaning that you're just computing some off-shell quantities that you're putting.
Off-shell vertex.
Yeah.
So the question is the approach? I mean, this is what you, as you told,
Yeah.
it's an amazing reduction of
Yeah, yeah.
complexity, right? In comparison to
Yeah.
standard Feynman diagram computations. So I would like to use it for, call it a general non-perturbative cross-section of product.
Mm.
In terms of representing this,
Mm.
is call it W-Young-Mills expansion.
Mm.
Is it helpful? Or is there implicitly some on-shellness going on?
I mean, there's on-shellness going into the, say, cut, in the sense that you put, but I don't think, if it depends what you're interested in. If you're interested in these long-range contributions that we talked about, I think inside the diagrams, like the lines, so we consider somehow diagrams like this, where you have some lines of, say, propagating gravitons here. And what we do is we cut these, we make them on-shell. The external states, you know, in principle, we could keep not on-shell. We don't have to specify them too much. I mean, they could have some structure. So I explained a scalar here, but it could be a photon or something else, the external. So I would say it helps us a lot to put these lines on shell, basically making, say, this is L, making L square equal to 0, and then extracting from that the pieces of the integral that are long range. But you would not like that. You would like to avoid that. But then, I mean, you could probably avoid it. So you could say, no, you could be completely off shell. But you would still have like long range. But now you would also probably have some short range stuff.
Yeah, one it all.
And you want both of them.
Yeah, and it's not about computing them analytically. I just want to know whether this approach for the W-Young-Mills is helping me to, if I want to use Feynman diagrams, but with full numerical propagators. Right? Is this helping me to reduce the computational cost of doing the algebra?
So you're asking if the double copy helps you?
Yes.
I would say it does, but it is also more complicated. If you are doing off-shell, well, off-shell is, I mean, you can do it, but it's not, I mean, there's a lot of additional stuff you have to consider. I would suggest something else. I mean, I would suggest you do this and you extract these pieces here. And then if you want to do this, you can still find them here, but then you know what they are from the first computation. So do it in 2 steps. And then that would allow you to maybe specify these in an easier way. But I would do this one first, because one can show that if you go on shell here or you work off shell, these long range are gauge invariant stuff. So
But nobody is.
well, we have done it at one loop. We have computed them both off shell and on shell, and we show they are the same. And if you don't want to specify helicities here, you can keep epsilons. So what you do is you do a trick where you just use that in each of these lines, you have a sum over epsilons. So you can replace that by propagator like Didanda. So by removing the epsilons and putting in a propagator here for the gravitons, you simplify this a lot. And that is actually easier, you found, than doing the spinor helicity, because the spinor helicity is compact but generates some spurious stuff that you have to remove. So this is easier. So I think it does help, but I think maybe not in the sort of, you have to maybe do some steps where you break it down and focus on some pieces first. You can see.
You said it does help, I
When you go off shell in such a way that you can complete the loop.
Yeah.
But I don't know if you can go off shell whether they complete or the issue.
Which I know.
Yeah. But you still get it. I mean, if say you're doing this and you're using the diagrammatics, like things like IBP relations and other things for the integrals, you're getting that advantage. So that is helpful also in the off-shell, because doing off-shell and the full tensor integrals is hard. But if you map to a basis where you know the transformations among integrals, you can do things faster. Yeah.
It's exactly like in string theory. You know only the full shell, but then nevertheless you can compute the
More questions? Yeah.
Once again about positivity bounds. If you start from the ultraviolet completion for gravity or whatever, and you compute the Wilson coefficients out of that, and you check that they violate positivity bounds, is there a way I can disentangle the origin of the violation? So whether I'm violating the unitarity or something else?
Unfortunately, not that I know of, because when you do what I showed at the beginning, you have all the assumptions. All the assumptions are necessary to get the bound. You need unitarity, you need polynomial boundedness, or if you want a Frazar bound locality in the UV, you need all of them. There might be a way, I mean, people have developed many different positivity bounds nowadays, of relaxing some of those and still getting bounds, and then comparing, okay, well, there's the positivity bounds assuming this, and there's positivity bounds assuming that, and then if it satisfies one or the other, then you could know. But just having one set, you can't disentangle.
Different sets.
Yeah, or then you can also maybe use causality bounds and say, okay, well, does it fit into causality island and not in the positivity? Maybe what is breaking is not causality, but other the assumptions of the positivity bounds, like unitarity, locality in the UV, and so on.
Then
So
in each case, so what type of assumption did you relax in these other calculations? So
what assumption did we use for the positivity bounds? So for the scalars, you can assume that there's a small mass, or that so you have a Frazar bound, or that there's a UV theory that actually makes the polynomial boundedness. That's what you need for the shift symmetric scalars and the other standard unitarity causality assumptions. For the photons, depends. We can have different assumptions. At the end of the day, the bounds that I showed were included just standard assumptions plus with coupling just to get rid of the loop corrections, but you can also include those. Anna would be more the expert on those. But
pretty weak, they were derived analytically and such that we know what is behind the bounds. What's behind the bounds is that they are infrared safe, so they are not sensitive to the presence of loss. They are probing Wilson coefficients around the scale of at the scales of order capacity.
But everything else were just like the standard assumptions that I mentioned at the beginning, just the unitarity. You do assume that there's locality in the UV, the polynomial boundedness. That's an assumption when you work with massless theories. So.
I mean that in gap theories, the bounds will be stronger, but some of the bounds disappear because of exactly the presence of these IR bounds. But in the case of gravity one, you have all of those assumptions.
In which one?
U1 plus gravity.
Right.
You would have like unitarity.
Yes, if you start including gravity, you need more assumptions. Especially if you want to look.
Just the quantum gravity would predict non-locality in the UV, so they might violate because UV bounds. And it would be nice to like to put a bound on how much you don't violate.
There have been different approaches to the positivity bounds, including gravity, that require less assumptions, which, I'm going to forget who was it. Is Julio Parra, Simon Stoffin. What they do basically is in that integral for the dispersion relation. I mean, there's going to be problems when you actually take the forward limit in gravity, because when you take t equals to 0, there's going to be a t channel, and then it's going to diverge. So you can actually put a function there to cancel those divergences and massage your dispersion relation, so you have less divergences, and you can actually do the integrals in the gravitational case without additional assumptions. And they have put bounds on this. So there are some bounds for gravity with less assumptions, if you want.
More questions? Yeah.
If I understood well, last week, John Dungy told us that the dependence of the gravitation, the bending of a massless particle implies an arbitrarity in defining the black holes.
Yeah.
Is it true?
So you mean specifically in terms of the bending of light that I explained, or?
I mean, if I define light cone using photons or gravitons or different particles.
I mean, there's a sort of IR regularization cutoff that you have to introduce. I think in principle it's no different from what you have in QCD. I mean, you can fix that from comparing to some experiment in principle or something else, or do a higher order computation that fixes that. I'm not sure if that's what he was specifically.
No, the numerical coefficient is different depending on the type of particle.
Yeah. So okay, so that's the difference in the different bubbles. So I mean, this is the same thing as we see for the bending of light. The bubble coefficient you have for. So depending on which particle you put here, when you have something like a diagram like this, that coefficient of that piece, it seems to differ between scalars, fermions, and photons, and in principle, other particles. So there's some difference in the amplitudes between the various particles, which doesn't follow the same universality you have for the classical components.
Then we give that some implication how to define the causality bound.
Yeah.
I actually have a comment.
Yeah.
So there's a thing when you want to define actually like light cones and the speed of sound in these theories, because the speed of sound is not an observable and it's not invariant under field redefinitions. So you have to be careful also when you're saying things are superluminal. Like if you look at gravity, you can actually look at the two modes of gravity and they will look superluminal in some case and not in other case, but this is not telling you actually things about causality. And that's why you should be looking at observables, like time delays or spatial shifts and so on, things that you can actually measure. So sometimes you cannot infer things directly just by looking at light cones. You have to look at observables. So if there's changes directly in the light cones, it might not immediately tell you what's the actual physics.
Let me briefly follow up on that. Can I maybe see this non-universality at one loop as the fact that different spin particles can couple differently to gravity non-minimally?
I mean, it could be. It looks like that there's some differences. Like there's a non-universality in the various couplings, and if you naively take that into the bending angle, which you can, you would say that you have different bending for the different particles. The reason why that might be too naive is this formula for the iconal. So we had the quantum component in the phase, and then we have the classical physics sitting in the phase shift. And actually, when you do that separation, you could say that the quantum effect is just a phase thing, but they will still have the same bending because the phase shift is unchanged. So it looks more like that it requires maybe a better understanding of how quantum physics interact with spinning particles. And that's an open question, but yeah. Yeah.
Yeah, I need to also understand this, because of course, so what you're saying is that scalar, fermion and photon classical for, I mean, if you try to make some classical link, this will be for different.
Yeah.
So if I remember correctly, like for instance, even classical, they just take a ball that's spinning. A ball that is spinning will not just follow a simple equation, follow this Matheson-Kolopelka equation. The standard left-hand side, the left-hand side, we have the Riemann tensor times some spin tensor. The part of Java momentum that takes account basically. And the similar equation also comes out if you do some like WKB analysis for fermions coupled to gravity. Basically, at the leading order, you will have some condensing equation. And the next leading order, you will get some correction to the geodesic equation, which is the same as the classical Matheson-Kolopelka equation. So I wonder whether one can really. So basically, what happens there is an interaction between gravity and spin.
Yeah.
I wonder whether this is something that is somehow related to that, or that we figure this one out.
I mean, we just see in the amplitude that this component is different, and the bubble diagram. I mean, this is what we speculated. Is it related to, say, UV cutoffs, something like this? Could you imagine like some theory that maybe remove the UV cutoff would be universal, like put in some supersymmetry, something? I mean, we couldn't come up with any reasonably good answers, but I think in terms of interpretation, you have to see the quantum effects, even though it looks like it's of the same order of magnitude as the classical, as something different. It generates different physics, and therefore it's too naive to just think of it as something you could just add to the classical. It's something you have to treat in a different way. And it could be that it's just some phase effect, and actually it has no physical consequences, and therefore you would preserve all what you know from GR. But of course, we can't just describe quantum gravity using GR. We need some kind of extension. So there's something there that needs. I mean, I think you have to think of falling in a quantum gravity, right? That you're actually sort of following different geodesics, and there's some kind of weighting of how you're actually doing it, and it must play a role there, right? But exactly how and the details of this requires more computation.
I'm not sure. This has to do with the comment that your work and talk about the using effective field theory to predict the Newtonian, the quantum correction to the Newtonian potential.
Yeah.
Supporting 1G.
Yeah.
There's really two scalar potentials in gravity.
Yeah.
And you get the other one, and what is it? And in particular, does it obey that the gravitational slip is equal to zero the way the classical general relativity does, or is there a non-zero quantum slip? So
you talk about, I mean, the potential, we talk about the standard sort of PM potential, but the other one would be, what do you mean exactly?
For example, if you used a particular gauge, one of them might be the deviation of the G00 component from flat space. The other would be the deviation of the delta IJ part of the potential.
Yeah.
In principle, two different potentials. In general relativity, they have to be equal to each other. In principle, they can be different.
I mean, I think you have to be careful when you talk about the metric like G00. There's a clear gauge dependence, and how to go from amplitude to the metric involves dealing with that, while the potential that you get from the PM, which is based on the matrix element itself between the external particles and some interaction, it's basically based on the amplitude, which is on shell and has no gauge.
I don't think that also change the fact that there's still two distinct general relativistic potentials.
Yeah, okay.
And there must be a second one. Can you get it? And does it obey the gravitational slip is equal to zero?
I mean, I haven't tried to do it. Yeah.
Would that be different if you're just considering that your source is a point particle? Because with the amplitude, you're always going to be considering that your source is something localized, like a black hole.
If the particle be relativistic, they would couple differently in principle to the IJ component than to the 00 component, I think.
If I just consider a black hole, these two will always be the same. Then that's what
in general relativity they are.
Yeah.
But in modified gravity theory, suppose I changed gravity, it wouldn't be. And quantum corrections, of course, do induce a modified gravity theory. And I think if you took the source particles, the dashed lines in the diagram, first of the diagrams on the left-hand side, I think if you took them to be particles that could in principle be relativistic or containing spin, I think you could probably distinguish the two potentials. I just wondered if you've done it.
No. I mean, there's an interest going to the metric. I mean, in the sense of using the metric as another definition of potential. I agree to that, but
you don't need to use the metric. There should be an observable where you can extract that the difference.
Sure. I think it should be done the same way as the.
So it's not to compute the metric, but to compute that observable from
calculate the amplitude.
Yeah.
Then assume that you had a quantum mechanical particle going in with certain properties, and you say, okay, suppose they had the same scattering amplitude. what would be the potential to cause that scattering? The same inverse scattering theory that we did to get the Newtonian potential.
Okay.
And I think if you had the source particle that was doing the scattering contain spin or possibly be relativistic, you probably could distinguish the extra potential.
Okay. Okay. But I think it's different. I mean, how to incorporate the quantum effects. I think you end up here where you basically have to distinguish between what actually exponentiate and what is phase and in the observables. And so the quantum effects are not easily put into, I mean, there will be sort of a backbone of classical effects that obey everything that GR obeys. And then you have the quantum, which somehow builds on top. And we are still looking for a good way to interpret these things on the top. But there could be something there that could be interesting to investigate. Yeah. Yeah. Yeah.
Of the potential coming from scattering amplitude with the potential potential from the negative is in the sense that in one case you are computing an amplitude between interacting fields that are even massive and the potential that you expect from the negative is the potential of a test particle, which by definition.
Isn't that the basis of inverse scattering theory? Isn't that the basis of inverse scattering theory? Isn't that how that's done? How that
No, I mean
the
potential, the invariant potential that you extract from the matrix is the potential on the test particle. So something that is massless, non-interacting. So it is a really different thing.
I think it's a potential on a massive particle, and I think it is done exactly the way I said. You pretend that the same quantum field theory amplitude that you got was the amplitude you would have gotten in quantum mechanics by coupling a particle to general relativity, and then you say, okay, what would I have identified the potential as to get that same scattering amplitude? It's called inverse scattering theory, and I think that's what they did. That's certainly what John Donahue did.
The point is the phi is the potential that is generated by the black mass, acting on something that it doesn't react on the space time, so it's something it has particle which is massless and non-interacting. So the things seem to match in this very the simple case of
what black hole?
It's a matching of EFT.
Yeah.
Here you have an EFT with a point particle, there you have an EFT with a scalar. You can match them.
And I mean, just the black hole, for example, like let's not even go to modified gravity, let's just add the cosmological constant to be able to the amplitude, and of course, washing the system, they are two different things that don't touch.
But what we're doing,
Don't disagree, so what?
It's not about the core, like about some big fields.
No, but I mean, a black hole, if you go faster away, that's essentially a mass.
Are we talking about the same thing? I'm talking about the original.
It would just be like a one-to-one in a black hole.
yeah, that's what I mean. So this is just on a non-trivial background, but just a particle probe feeling it, and this would be a 2-to-2.
Yes. Matching between different.
Yeah. And we use this, of course, to. Yeah.
Maybe they can also comment.
No, I'm just saying that, I mean, what we do is we compute the 2-to-2 scattering process. So you have two particles interacting, coming out two particles. But you can also transform that into a one particle description on a non-trivial background. And that's what we do. We use this equivalence to.
You say then what potential
would that correspond to in either quantum mechanical sense or in terms of a metric in GR?
That's the inverse scattering.
Yeah.
And the point is that there's two general relativistic potentials that the particle could have coupled. Two independent scalar potentials. There must be a way to distinguish them. They are the same in general relativity, but they don't in principle have to be the same. But
the reason this is easy to work with is that here we can take time to minus infinity and infinity, and we are in flat space. So we can start at asymptotics, and then we can compute. So that gives us a very good link to S matrix. But here, since you're on a non-trivial background, you have to, it's harder to define. Yeah.
Exactly the same thing. I think you could say, okay, suppose I had a point particle that was coupled to a background general relativity that has this particular potential. What potential would I have chosen to get the same scattering?
Yeah, that you can do. But to say you wanted to compute this from first, this you could say you don't have to compute from anything else but the Lagrangian of GR and the states. But this one you would infer from this computation. That's what people do.
Right.
Yeah.
Infer what the second.
But this is what people do. So this in the post-Minkowskian is what's called EOB, one body effective potential. Yeah. But this gives you actually stuff that I mean, in some sense, it allows you to determine non-perturbative aspects of the in-spiral when you come to like these black hole mergers. So there's a whole program there to compute these things using this to.
Very interesting. We're interested in the G over R squared fractional correction. There must be two independent potentials, and I'm pretty sure you can get them using inverse scattering.
Yeah.
It's not clear to me that they'll be the same, but maybe they are.
I mean, I think the way you do it is you do this, you construct the iconal. Once you have the iconal, you can deduce this because there's a link. So the scattering, the delta theta, the scattering, has a formula that depends on this EUB potential. So you can use that to go from this delta bending angle to a EUB potential, because there's a formula linking what is the bend. Yeah.
Difference. Results.
You can see what should be the potential that would give you that bending angle. Yeah, so that's what people do.
Has it been done?
It has been done. People are deducing, in some sense, an effective metric from this that you could use to.
What's the result? Two potentials the same the way they are in classical general relativity? Or
So this is what I'm saying is people are doing this computation and deducing this one. But I think this one has not been done in an honest way, like from computation. I haven't seen that. So if you compute the metric here and you do it, and that's hard to do fully relativistic, but you can do it order by order Newtonian, then you can from that metric, you can see how that would feed into this EUB potential you deduce from this. So partly it has been done, but I don't think it has been done.
Perturbative thing. You can just do it perturbatively, and perturbatively it has been done.
you just needed to order G, the order of the fractional G over.
Yeah, you don't need to hold on perturbative thing to match these two potentials in the way he's thinking. Just make the perturbative version.
Okay.
And I think everything that has been done has those two being the same.
The two potentials are the same, so they have zero slip.
But in principle, you can assume this is not the same, and I don't know what you need to have on your theory on the gravitational side to make them different. But if you already know, you can put them in there, compute the scattering amplitudes, to matching just at the level of the scattering amplitudes on both sides. Like scattering amplitudes of point particle versus like standard QT scattering amplitudes, and you should be able to read off the matching principle.
Yeah, I would think so.
Like,
But maybe you, Paolo, know. So
I think that we are talking about two different potentials. I mean, you want the potential which, if you start from the scattering amplitude, you have to go in the probe limit. The probe limit is a very special limit of the scattering amplitude. It's not,
yes.
Now, you are talking a potential that you extract from the scattering.
Yeah.
Which is in principle, there is no probe limit in your case.
Yes. You can only do that matching in the probe limit. Yes.
Yeah.
And now, from there, you are describing here how you extract observer from the icon. Or if you want, how you extract the classical icon. But there is an equivalent procedure where you extract the potential. But the potential that you extract with your recipe is not the potential that he wants to get. Because in your case, it's only the problem. The problem, it means that one mass is much bigger than the other.
Yeah,
The Bohr perturbation.
I guess so, in the sense that it's a source, but couldn't you deal with a quantum mechanical problem where you had two particles that had similar masses or even one relativistic? You deal with a scattering amplitude?
Yeah, that's the potential that he's talking about.
That's right. Couldn't you solve that in quantum mechanics and then just use inverse scattering to return what the relativistic potential would be? The actual potential?
But wouldn't you lose track of actually, yeah, I mean, here it's very intuitive to see with the core background how you have these two different potentials and so on. If you actually do the quantum mechanics version, is it obvious that you're going to...
Couple of quantum mechanical particle of different spins to general relativity. I think we know how to do that, at least for the simple.
In the case where you're going to have non-zero gravitational slip?
Yeah, I think so. Why would we not? If we know how to do it in a general method, then we know how to do it. For example, for a scalar, it's just square root of minus g mu chi dot u chi dot u. For a spinning particle, there'd be an extra term.
Yeah, sorry, maybe I'm not understanding the setting. Are you trying to put the two quantum particles in a curved background? Oh, no, then again, it's not the same matching. Because I think here, what you're matching is that this curved background is what's being generated by one of these black holes, and the probe particle is the other particle that's scattering. So
you can, this is what I'm saying, from this computation, you can rewrite that in terms of something like this, where you write down some metric, which you say is an effective metric. It gives you sort of an effective background that will explain, or in the same way, the 2-to-2 scattering process.
Right. Well, one of those massive and one might be.
It doesn't matter too much because, you know, you could have a diagram like this, where this is the one, this is like a probe limit, where all the propagators are sitting on this side. So this would give you something for a small mass on one side. What you do in this process is you resum all the diagrams, so you have all the mass ratio terms in your computation. So you're not actually in a probe limit, you have separate contributions for each of the different mass orders in your computation. But then by computing what you do is you can compute the bending angle here, and you can compute the bending angle here, and you can require that these two match. And by that match, you define a potential in this curved background that's giving the extra potential, and it's fully relativistic. And this has been done. This is what people are doing to describe the inspiral of black holes. And
they get a slope is zero, or they get a non-zero slope?
That I don't know if it has been analyzed, but maybe Moore would know.
Effective one body.
Yeah, effective one body. Yeah. But what I don't think has been done is to work exactly here and define a theory that would work here. Because I think then you don't have asymptotic states. It's hard to do an S matrix. I mean, maybe something can be done, but yeah. But when Veneziano, Damour used the string result to compute the EOB, is that a way to generate the EOB potential without having to do the 2-to-2 scattering?
I mean, he writes, you know the S matrix,
Yeah.
and then you construct an effective theory, where you have Schwarzschild, an effective theory that gives the same result after the calculation. That's what is called effective one body method, which has been used to also compute templates for LiDAR.
I think that for what he wants to do, you don't need the whole effective one body. You just want the leading corrections.
Yeah, but that you can get. So this one,
you can do exactly what like you said. But
Yeah. So this is a sum over, say, mass ratios. And there will be some leading coefficient in mass ratios. That's the probe or the Schwarzschild. And then there's a next to leading coefficient to that. That's somehow a sub-leading correction and stuff. And you can match, this has been done to match Schwarzschild and the first coefficient in the EOB. So people have done papers resumming and finding all the corrections from Schwarzschild and showing you get exactly the Schwarzschild solution if you start from a perturbative framework. Duff did it, and then there's been follow-up papers, more explicit, where they go beyond. Duff does something like 2-3 loops, and now it's down to all loops.
I think that's just checking the classical potential.
That's still classical, yes. Yeah. The quantum corrections as said. Yeah, okay. Yeah. So you could do something like this, but I think there's still this issue of defining somehow a good way to, I mean, if you should actually include the quantum piece in the potential or not, I think is an open question. I think you should think of, it's a bit complicated to make a physical interpretation of what the quantum piece is, because in the icon, it's more like a phase than it's actually a physical observable. But yeah, maybe we can talk more.
Okay, more questions? Hello.
Probably you can, I mean, you can put this, instead of putting downstairs, you can put upstairs.
I mean, this is what you could do, but I thought that one idea behind writing the iconal and keeping the quantum.
So suppose that you put upstairs,
Yeah.
you define an iconal which has also a term, it's not 1/h bar, but order 1.
Yeah.
And then from there you compute the deflection angle.
Yeah.
Do you get what you wrote in your transparent?
I mean, this is what we did in that paper. I mean, we just said, suppose you take the iconal framework and you just include the quantum naively, then the piece that I wrote is what you put into the iconal. That's a shift of the stationary state. Yeah. But some people argue that that's not correct, like Paul Dambo doesn't like that. So.
I mean, it's like when you do the path integral, you have exponential of the classical action.
Yeah.
And then the quantum correction downstairs, I think you can put back up.
You can, yeah. I mean, I think what you said yesterday is that, I mean, 2-loop has been done, I think, exactly, and keeping all the pieces. One should compute the 2-loop exactly with all the quantum pieces and see what happens in a 3-loop. How does that iconal look with everything? And that would be a good computation to do.
But there are all the amplitudes, so it should be computed.
Yeah.
It's just a question of sitting down.
Yeah, and doing, yeah.
Any more comments on this? Yeah.
Something we can extract this potential and eventually this can be compared with 5. But so for instance, just going to the gravity, if you have the technological constant, the matching doesn't work anymore. Of course, we are simply checking the asymptotic structure, and that maybe that's where the issue comes from. Right.
Yeah.
You feel have an inherent potential and just simply like the standard correction between the Steelers watching method. The things you do not touch.
I mean, I think only thing has been done in this vanilla type gravity where basically these things with cosmological constants and other things has not been touched. But putting in effective operators, I think, is possible. doing things like modified gravity then would be possible, because you could rewrite in terms of some effective operators. But cosmological constant is one of the questions in the effective framework that one should address or maybe make. But I think for these type of applications where you're doing black hole scattering, you can ignore it, right? But if you're looking at some other effects, maybe cosmological, you might have to account for it somehow. I'm not sure what to.
I think that for generation of gravitational waves, which is what this is computing, you can ignore that you're living on the Cedar or expanding universe, and you only care after the generation. You just care about when it propagates. That's when it's important. Waves, whatever.
That was justify
Mhm.
what you say. Maybe it is non-trivial to go from that potential that corresponds to the amplitude to the phi of the metric. I mean, it's not always possible to.
No, I don't think it's always possible. I also think that this is somehow you're doing some choices, because when you make this match, you are matching something that's actually a formula that involves an integral, and it's possible to put terms that gives you the same angle, but it's actually not the same metric. So you have some freedom there. So you do some choices for how you want your metric to appear, and it gives you an effective metric that may or may not be too physical, but gives you the right physical results. Yeah.
I have a few more minutes left. Any questions? Maybe I can ask one about positivity bounds. You mentioned during your talk, and it was a brief question, that you mostly focus on 2-to-2 scattering, and that higher order, like more particle scattering, is really difficult. So, but what is really the difficulty? Is it more like conceptual difficulties or computational?
Technical difficulties. When you have 2-to-2 scattering, you're just gonna have your three Mandelstam variables, and then you have momentum conservation. So just two. Once you have end-to-end scattering, you have first more Mandelstam variables. Second, the analytic properties of the scattering amplitudes are not well understood for end-to-end scattering. So the whole idea of positivity bounds is doing this dispersion relation, I said, and for that you actually need to know the analytic structure in the complex plane of one of the Mandelstam variables, and it all just breaks down once you start doing more. It just, people don't know a lot of things about the analytic structure in that case.
I see. And maybe can one learn something from exactly known theories like CFTs, that okay, I have this exact theory, and now I can compute, I don't know, 2 to n, and then maybe get some info or at least some idea from that?
I'm not entirely sure if those would be useful for once you move away from CFTs, just because the analytic structures can be entirely different, and that's basically the problem, just the lack of knowledge of.
So I want to add that in principle, if you're interested in 6-point vertex, bounding the coefficient of random 6-point vertex, you can still get it from 2-to-2 scattering, because it will contribute to the of course, there are some consideration of the diagrams, and then you simply apply same technique. In certain units, you can get it.
Yeah, I guess in principle, you could also do the same for higher point if you just can construct loop.
Sometimes maybe up to 2 loops.
Yes, and
then it's just a technical problem.
But I guess you also need to know again now the analytic structure. Now, when you include these higher point vertices in your loop amplitudes, is that all?
Such that one of these vertices is contributing, like one of the vertices inside this loop diagram. So the analytic structure then is it's then we simply compute,
Mhm.
calculate whatever what are the tools for that, and then you can write same description relations and adjust them such that you make them sensitive to particular conditions in terms of local or more computer.
Yeah. Yeah, I guess as you say, it's just technical difficulties because now you're gonna have many branch codes. So
It still is you can make new.
Yeah.
Sometimes they prevent from getting bounds for certain conditions, but not all.
Okay. More questions? Maybe one last one.
Your amplitude that you study, you take the low energy limit.
yeah, basically everything is low energies.
And you try the high energy.
No, because I'm mostly working with effective field theories, but I guess that could be done if I have a UV completion. But I don't expect any changes. If I'm working with a UV completion that we know is physical, it's just going to be causal by default. So I'm not going to find anything interesting.
But that means if you consider the theory that you consider, they will be inconsistent at high energy.
So if it's one of the theories that gives rise to a causality, most of these, there's not known UV completions for them. So that exactly because of that, because you expect it to be inconsistent.
Last chance.
Yeah.
Yeah.
There, several you can compute because you're working in a larger set of theories than just the quantum string theory.
Yes.
So can you use the relaxed assumptions to study how something goes wrong when you go in the high energy limit and have a classification of why certain theories are not compatible with string theory by looking at some behavior at high energy or something?
So the thing is, for the causality part, all the calculations are done at low energy. But if you have a UV completion in mind that is different from string theory, you could compute, I guess, an effective field theory for it, or not even that. You can just check the causality properties. But to distinguish between UV theories, I mean, this is only going to distinguish between the low energy regime. It's not going to tell you anything about the high energy regimes. But I think
I have to put in by hand. In any case.
You have to choose. Yeah.
I mean, what helps in string theory, high energy is a Regge limit that you don't have. Yeah.
Yes, exactly.
Good. I think it's time to thank our two speakers again.